Hello, and welcome to my submission for video project number 2. Today we will be working on separable differential equation and an application problem, which is actually also a separable differential equation, just a specific case of one, a little more based on some real-world situation. We're going to go ahead and get right into it. Here is the equation we're going to be working with for our separable differential equation. It's a little involved looking, but it's not really that bad. Of course, all these terms here, they're all kind of mixed together. So what would the first thing we need to do be? You might think that it would be to factor out these terms, and that would be exactly correct. Factor them out, it's pretty easy, and you get these two binomials. And of course, we could factor out this x here if we wanted to, but it won't actually help us much, so we'll just leave it in here. And now, of course, since these two terms are only have one variable each, they can be split apart along this multiplication here. We can do division and multiplication of terms across the equal sign to get all of our y's on one side and all of our x's on the other. And if we do that, we will get this. Just the 1 over y plus 1 dy on one side and the x squared minus 4x dx on the other. And the parentheses here don't actually mean anything. They're just to make it look a little more clean. Otherwise it looks like the dx gets mushed right onto the end there by my software. Anyway, once we have this, it's pretty obvious what the next thing to do is, right? We integrate, just like so. Of course, all I did here is add the symbols, so we got to actually do that now. And when I integrate these things, what do we get? Well, we get the natural log of the absolute value of y plus 1, and we get x cubed over 3 and minus 2x squared, because 1/2 of 4 is 2. And we have a c on the end, but it's labeled c1 because, well, of course, any integration will result in a constant output. Both of these did, of course, because they are integrations. But since a constant is a constant and a sum of constants is just as much a constant as any one constant is, we just moved them all over to the one side and named them C1, because that way we can keep track of where we are. Anyway, the next step is to, of course, raise both sides up into the exponent of an e. That way the natural log can be taken away, and we can start to get to our general form. Now, what I've done here, I should have labeled this C3, because I've done two things in this, two changes to the C here. So it's not just C2, it should be C3. The first thing is, of course, that e to the C1 is still a constant. It's a different constant, but it would still be a constant. We could call that C2. After all, these terms are in the exponent. They're connected by addition and subtraction, which means they correspond to e being multiplied by e to these other terms. E to this term times e to this term times e to this term is also written like this. So anyway, because of that, this e to the c can be written as e to these two times e to that one, which is just we're going to call it C2, and put it down as a coefficient. But then we're also getting rid of the absolute values, so you would say, oh, it's plus or minus C2, but okay, we could just call that C3. It's still a constant, positive or negative, or both a positive number and a negative number are both just as much constants. But that's no big deal. We just go ahead and do it. Here we are. Our last step, of course, is to move this 1 over to the other side, like so. Subtract 1 from both sides, and since we're not changing the constant anymore, we just get rid of the subscript. It's just C. Now, if we hadn't been given a y naught value here, then we would be done. But we have. So why not find out what c would be in this case? Well, easy enough. We just plug in 41 as our y value and 0 as our x value. And this gives us 41 is equal to c times e to the 0 power minus 1. A to the 0, of course, is just 1, so what we really have is 41 is equal to c minus 1. If we add 1 to both sides, we find out that c is 42, the answer to everything. And we plug that back into our general form up there, and we get our specific form for this case, which is y to the x, or y of x, is equal to 42 times e raised to the x cubed over 3 minus 2x squared power, all that minus 1. And we're done with this example. Like that, box the answer. And now, for my second problem, for my application problem, I've picked this. I've got here a little story. It tells us that the queen prefers to drink her tea at a temperature of 130 degrees Fahrenheit, but that it is brewed at a temperature of 212 degrees. Over the course of 5 minutes, the 5 minutes that it takes to brew, the temperature will only drop 4 degrees to 208 degrees Fahrenheit. If the palace is kept at 68 degrees in the winter, when will the cook need to start the tea brewing so it is ready on time at 3:45 p.m.? Well, here, I'm going to probably get in the way if I stay down here, so I'm going to move. There we go. So the thing is, what is this? What are we looking at here? We're looking at something cooling. So we need to use Newton's law of cooling. And we know that we need to use it. So here it is. In this case, I've labeled the temperature of the surroundings Tp for palace. But what is the Newton's law of cooling? Well, it's telling us. What is it telling us? It's telling us that the change in the temperature with respect to the change in time is proportional to some constant multiplied by the current temperature value at whatever time you're talking about minus the temperature of the surroundings. Or rather, to put it a different way, the rate of change here is a constant times the difference between the temperatures. So the more similar they are, the smaller this whole value gets, because, well, if we were to get down to 68 degrees, 68 minus 68 would be 0, k times 0 would be 0, and the temperature would stop changing. But anyway, as I already did by pointing at it, we need to put that 68 in there, and now so we can start to solve it. And we should probably also note down our actual values for the different times so that we don't forget them. So we know at time 0 the temperature is 212, and at time 5 minutes the temperature is 208. Knowing these things will be very important later, but for now we just need to find the general formula of this differential equation. And so, just like with the previous problem, we need to do some multiplication and division across the equal sign to separate out our terms in a convenient way. We could put the k over there, but it wouldn't help us any, so we don't. In fact, it probably wouldn't help us much at all. In fact, it wouldn't help us at all, because it is just a constant. It would be still floating around connected by multiplication. Anyway, this is integratable, so we will integrate it. And the result of integrating this part is very similar to the previous one, only a different value here. It's tk instead of multiples of x cubed and x squared. That's fine. This is actually easier. So now we have a natural log, and we have a value, and it's C1 because it's the sum of the C's, just like last time. And we'll just raise everything up into the exponents of some e's to get rid of our natural log, just like before. The C1 will become coefficient C2 for the e, just like before. And we'll get rid of these exponents by saying C3 is equal to plus or minus C2, just like before. Still just a constant. What exact constant it is doesn't really matter for this, at least not yet. And now that we have gotten this far, we're basically there for our general form with two variables with a couple undetermined numbers in it, but we will determine them. So we just go, all we have to do is we add that 68 to the other side, and we get our general form. The temperature with respect to time is equal to, or the temperature at time t is equal to C times e to the tk plus 68. We should go ahead and plug in our first value, our temperature at time 0, because that makes e go to 1, just like this. E to the 0k is just e to the 0 is just 1. So 212 is equal to C plus 68. Subtract out the 68 from both sides. C is 144. Nice. And having that value means that we can refine our formula. Now we have a more specific, but not quite exactly dialed in, form of our solution. We just need to now figure out what K is. It's going to be very small because this pot seems to do a very good job of holding in its heat, only cooling 4 degrees in 5 minutes, in the first 5 minutes. Anyway, all we have to do here is plug in our other given value, the temperature at time 5. And once we do that, we will be well on our way. So we do that. Temperature at time 5 is 208 degrees, and that is equal to 144 times e to the 5k plus 68. We do some basic arithmetic here, nothing too fancy. 208 minus 68, of course, is 62. No, that's not right. That's later. I'm misremembering. Let's just show you. It's 140. 62 will come up again. I was getting ahead of myself. So 208 minus 68 is 140. Divide that by 144. And yeah, obviously we have this fraction is equal to 5e to the 5k. We need to get rid of that e. So we'll just make everything a natural log. And then that means we got rid of the e. We have 5k. We have to divide the natural log by 5 to get what k is. And so here we are. The natural log of 140 over 144, all divided by 5, is equal to negative 0.005634. And that's our k value. And now, finally, we're on the home stretch. We just need to put that into our general form, and along with our c value, and we get this lovely thing. And we now need to use it to solve for t when, what time will the temperature be 130 degrees. We just plug in our 130 and we get to work. And the steps we need to take here are almost exactly the same as the ones here, it's just some different numbers. So we'll go ahead and we'll subtract the 68, divide the 144, and then take the natural log of both sides and multiply it by the constant portion of the exponent. And it looks like this. You can see 130 minus 68 is 62, 144 goes on the bottom, the natural log of the whole thing, and then that gets rid of the e, and we divide negative 0.005634t by that number, and we also divide the other side by that number, so we get this arrangement, and we finally get our answer in minutes, 149 minutes and 0.5 of a minute. So just a little bit over 149 and a half, 30 seconds. A little bit past 30 seconds into the 149th minute. And once we have that value, of course, now we're basically there. We just have to do a little tiny bit of basic arithmetic with our times to figure out, by dividing by 60, that 149.56 minutes is just 2.49 hours. And if we're looking at 2.5 hours before 3:45, well, that's just going to be 1:15 p.m. That's when the tea needs to be brewed in order for it to be ready to drink on time if we use this very well insulated pot that we have discovered in this problem. And that's it for that problem. Now this is not the problem I wanted to do. I wanted to do a more interesting, to me, I guess, because it wasn't in the class. I wanted to do something special. I wanted to do an application problem where the rate of the change of the angle of this here was determined by the speed of this passing object that it's pointing at. Well, what is this here? Well, this is my drawing of a coastal defense gun, and this is like an enemy ship or something. I went and visited the one in San Diego, and that's why I wanted to do it, part of why. But figuring out like which trig function to use and how to set this up so that it could be solved was difficult for me, and so I figured it'd be way too hard for Pikachu, so I'm not doing it for this video, and maybe not ever. Well, I still do kind of want to, but anyway, that's the end of my video. Thank you for watching, and have a nice